Hello, so in this video we will talk about non-deterministic finite state automata. So as opposed to a deterministic finite state automata, the main difference between deterministic and non-deterministic is that the next state is not unique. So next state can be nothing, or next state can be a set of one or more states. So a formal definition goes like this. So a non-deterministic finite state automaton, which is comprised of Si, F, S0 and F, where S is a finite state of states as in the case of deterministic finite automata. Same for I, which is the input alphabet, finite. And the mapping F is from a pair of sets and input to power set of S, where PS represent the power set of S. So this means what? How many states are possible? So remember, what is the cardinality of a power set? So if S has the cardinality n, then power set of S has the cardinality 2 to the n. Okay, so there are 2 to the n possibilities. Okay, and then S0 is again the starting state, and typically it's S0. Okay, and a subset of S is a capital F, which is denoting the final states. Okay, so as for deterministic finite automata, the representation is again by state table and state diagram. And for state table, we can all appreciate that changing this definition will have some changes to the state table and state diagram as well. So we will have more than one state or zero states for the next state column. Okay, now let's see an example to demonstrate what we have said here. So if we have a state machine, a state if we have a finite state automata which has to recognize all the string which end at 10, and it does not accept any other string. So we can say this is my starting string, uh, this is my three states, so I can say 1 here and 0 here, and I can say 0 1 here, and I can say this is my A, this is my B, this is my C. Okay, and then this is my ending or final state. Okay, so now note that there are transitions from A to B for 0 single transition, but there are two transitions from A for an input of 1. There is one transition which ends at A, there is another transition which ends at B. Okay, and the question comes whether how to select the next state. So the answer is, for now, the basic answer is that it is selected randomly. Okay, but note that if a 1 0 comes, then we can actually go to a final state and we can actually recognize that string. So note that the only time when we can reach a final state is when a 1 0 comes. Okay, so this actually satisfies or fulfills this requirement of accepting only those strings which end at 1 0. Now let's say what is the state table for this state machine. So let's say we have state A, state B, and state C. Okay, so what is the next state at input 0 and input 1? So at input 0 we stay at 1 A, at input 1 we can stay at A, or we can go to B. At B, if a 0 comes, then we go to C. So this is a starting state and this is an ending state or final state. For B, if we get a 1, then there is no option for that. For C, there is no transition. So once we are in C, then we are done. So this is the state table for this state machine here. So note the difference between a deterministic and a non-deterministic finite state automata. Now the question comes whether we can, given a non-deterministic finite state automaton, can we find an equivalent deterministic finite state automaton or not? The answer to this question is yes. And the steps involved to convert a non-deterministic finite state automata to a deterministic finite state automaton comprise of two steps. One is subset construction and then the actual minimization. Okay, now in order to demonstrate this, let's take this example. So we have three, A, B and C. So my S is A, B and C, right? So this means that my PS will have 2 to the 3, which is 8 options. So now let's make all those options. Okay, so my first subset is 5, empty set, then just A, then just B, then just C, then AB, then BC, then CA, and then A, B and C. So now if we are in this subset, so these are the sets and this is my input 0, input 1, and if I'm here, then again I have this and this. If I'm at A, then I'll just copy this. This is at 0 I am at A, at 1 I am at A and B. Okay, if I'm at B, then I have a C here and I have a phi here. If I have a C, then phi here and phi here. If I'm at A, B, then at 0 what happens? So if I'm at A, B, then at A 0 happens at 1, and for B a 0 happens, a 0 takes it to C. So this means I will have A and C at 0. Okay. If I am at A, B, then an input of 1 will take it, for A it takes to AB, for B it takes to a phi, so this is AB here, because I'm taking what? I'm taking the junior. So for BC, there's no, so for BC, an input of 0 will take it to C, and an input of 1 will take it to a null set, because this is a null set and this is a null set. For CA, I have A and AB, and for ABC, this is, for 0 I have AC, and for 1 I have AB. So this is the deterministic, and note that these are just labels, so I can just change this to, like, say P, Q, R, S, T, U, V, W, and this will all change. So this will be the deterministic finite state automaton corresponding to this. But this is very very tedious, because for only 3 states we have 8 states for a corresponding deterministic finite state automaton. Imagine we have 10 states here, so we will have to make a deterministic finite state automaton for 2 to the 10 states. So is there a way to actually reduce the number of states here? So the answer to this question is yes, but the answer comes from inspection here. So for inspection, what do we do here? So we start with the first one. Okay, we start with the first state A, and then we have at 0 and 1. So for 0 I have an A here, for 1 I have a A and B here. So the question is, do we have any new states in the first go? Yes, we have A, B. So immediately I will say A, B. This is my new state. So for A, B at a 0, I will just copy this. So we have AC, and this is AB. So do we introduce any new states? Yes, for AC. So AC, I'll just copy CA. So this is A and this is AB. This is A and this is AB. Now A is already there, AB is already there, and AC is already there. So this is my corresponding state machine. So I can call this one as P. Note that these are just labels, P, Q and R. So then my P And what are my final states? That's a good question. So my starting state is A here. Okay, so this is my starting state. So starting state, and since C is the only final state, so C is only here, so this is my final state. So R is my final state. So P, Q, and R. Okay, for P at a 0 I get to A, which is P again. So 0. At 1 I go to AB, which is Q. So at 1 I'm here. At Q, at 0 I go to here, and at a 1 I stay here. For this guy, at a 0 I go back to P, and at a 1 I go back to Q. Okay. So this is the finite state automaton, deterministic, which accepts the same language as this state machine, and we can check it easily that only those states which end up at 1 0 are accepted, because this is a loop here. So we have anything here, and then if we have 1 and 0, 1 and 0, only then we can reach the final state R. So this is it about the non-deterministic finite state automaton, a little bit about its representation, and a little bit about how we can find an equivalent deterministic finite state automaton given a non-deterministic version. Thanks for watching and hope you like the video.